Record. Okay. Let's begin. So we will we'll start with. So we already saw what a projection map was, or projection operator endomorphism is. Yeah. So let me just recall. So say you are given a subspace W of a vector space V. Then we always know that there exists, I mean, you can find a complementary dimensional vector space, yeah? Complementary vector space, not just complementary, such that W plus W prime is whole of V and W intersection W prime is 0, yeah? So in other words, V is internal direct sum of W and W prime. So once V is internal direct sum of W and W prime, you can map onto W. Yeah. So any element V in V is W plus some element in W plus some element in W prime, and that too uniquely because it's a direct sum, right? So you just send W plus W prime to W. So this is the projection map, but to call it a projection operator, basically you think of W as a subspace of V. So it becomes a map from V to itself. Yeah. So you compose it with this inclusion, then it becomes a projection operator. So if you think of it as an endomorphism of V, then it becomes a projection operator. So any element V in V, you can write it uniquely as W plus W prime, because V is an internal direct sum of W and W prime, where W is maybe I. Where W belongs to W and W prime is in capital W prime. Yeah. Then you send V to this W. So this is a projection operator. Any such map is called projection operator. So there is another way of defining projection operator, which is saying you take an endomorphism of V, which has this property that P squares, call that an endomorphism or linear operator P of V to be P, such that P square is P. Then it is again a projection operator. So we'll see that both these definitions are equivalent. Okay. So we'll see that any map which looks like this, that means it's projection onto a linear map together with inclusion followed by inclusion, is same, has this property that P square is P, and conversely, given an endomorphism which has this property that P square is P, we'll show that you can write it this way. Okay. So let's first prove that if you are given an operator like that, then P square is P. Yeah. So we are given a map. So we are in the setup. Yeah. So V is in V, and we are writing it as W plus W prime, where W belongs to W, and so we are proving the forward direction, if you like. Yeah. And W prime belongs to W prime. Yeah. So P is a linear operator. A linear operator P is a projection. Sorry, I haven't written it correctly. Projection if and only if this happens. Yeah. So now we are proving the forward direction. So we are assuming this is our definition in the first paragraph, and we are proving P square is P. Yeah. So let's look at P square of V. So what is P square of V? So it's P of V. Yeah. But P of V is W, right? And P of W is again W, because W you can uniquely write it as W plus 0. Yeah. And W we know is P of V, right? So we see that P square of V is same as P of V, and V was arbitrary element of V. So that tells you that P square is P. So I mean, this is not difficult. I'm just saying that one has to produce an argument. Yeah. And then conversely, if you assume P square is P, then I have to come up with a W and a W prime. Yeah. So W will be basically image of P, and W prime you can take it to be the kernel. Yeah. Of P. So conversely, conversely, suppose P square is equal to P is some endomorphism which has the property that P square is P. So take W to be image of P and W prime to be kernel of P. Yeah. Then of course, if you first thing is that W intersection W prime we'll have to show is 0, and their direct sum is V, that we have to show, and then we'll have to show is that P factors through this, and then we'll have to show that P is of this form. Yeah. So let take any vector in W intersection W prime. Yeah. So if you take something in W intersection W prime, since V is in W, it is in the image of P. So you can and it is in the kernel of P. So PV will be 0, and V will be P of V tilde for some V tilde in V. So or maybe I should write here for some V tilde in V. Yeah, because W is the image of P. Yeah, so if you take V in the image of P, then it has to be P of V tilde for some V tilde. Yeah, so now so we want to show that V is 0. So what you do, you apply P to this equation. V equals P of V tilde, right? So if you apply P to this equation, it becomes PV equals P square V tilde. Yeah. Apply this projection operator both sides. But PV is 0. Yeah. So this is 0. And P square V tilde is same as PV tilde because P square equals P. So here is where we are using the fact that P square equals P. Here is where we are using the hypothesis that the endomorphism has this property. And PV tilde is equal to V by our assumption. Yeah, so that tells you that V must be 0. So this tells you that the intersection of these image and kernel is 0. Yeah. So this happens only, I mean, it happens when it's a projection operator. Usually it need not happen. Yeah. Um, if you take a random linear map, this is not necessarily true. But for linear, projection operators, it happens. Okay, and then the point is dimension of V, we know by this nullity. Yeah, so for image and nullity, rank nullity theorem, for instance, dimension of V is dimension of W prime plus dimension of W. Yeah. So if you look at the internal direct sum of W and W prime, then it's a subspace of V, but by dimension reason, it must be equal to W. Yeah. So it's internal direct sum because their intersection is 0. So their sum is going to be a subspace, and you can write it as direct sum. But since the dimension matches, it has to be whole of V. It can't be proper subspace. Okay. So there are multiple ways of arguing why it is. So maybe dimension is the easiest one. So this is rank nullity. Rank nullity. We saw that a few classes back, yeah, that dimension of the vector space is same as the dimension. So if you are given a linear map from V to W, then the dimension of V is same as the kernel of linear map V. Then dimension of V is same as the dimension of the kernel of V plus the dimension of the image of V. So that is what we are using. Is this okay? Any questions? Okay, so once you have this, then of course PW plus W prime. If you take any element in V, which so any element here, meaning it will look like W plus W prime, it goes to W. Yeah. Because W prime is in the kernel, so that will get mapped to 0, and W. So P of W is going to be just yeah. So yeah, so I have to argue a little bit why it is P of W is W. Yeah, so again, you'll have to use, so one has to argue that on W, it acts nicely. Yeah. So you'll have to use something. So so it is clear that it is P of W, but why is it W is what one has to show. Yeah. But maybe it follows. Yeah. So it follows from so P square of W is P of W. Yeah. And so so this proves that P of PW is PW. Yeah. Sorry. So this last bracket is unnecessary. Yeah. So that tells you that for every element in PW, so that tells you that for all, so this implies for all W in image P, if you apply P to it, you get PW is W. Right? This identity proves that. Yeah. So that completes the proof. Okay. So that proves the other direction as well. Is that okay? That the project. So this, I suppose you may have seen this. That I don't know if have you seen this projection operators P square equals P. Yeah. So anyway, so this gives you the proof that projection operators are same as operators which has the property that P square equals P. Okay. Okay. So there's so remember in trying to do the Jordan form, we are trying to show that some linear operator, the matrix of a linear operator is a block diagonal matrix, yeah, with diagonal pieces of a certain kind, right? So to do that, basically, what given a linear operator, you would want to decompose the vector space into invariant direct sum of invariant subspaces. Yeah, because if you have that, then the matrix of the linear operator with respect to basis of these certain vector spaces will give you a block diagonal matrix. Yeah, so that is what we will prove next. Any questions so far before we get to this next result? No. Okay. So so this is the next result. So let phi be a linear operator on V, and W1 to WR be a phi invariant subspaces of V. Yeah. So we saw that if we take one phi invariant subspace, then how does the matrix look like? It looks like block upper triangular. Yeah. But now we are just extending the results to assume that it's generated by I mean, it's direct sum of V is direct sum of invariant subspaces. Yeah, then you will get the block diagonal. So W1 to WR are phi invariant subspaces of V. That means phi restricted phi of W1 lands in W1, phi of W2 lands in W2, and so on. That is what phi invariant means. So that V is the direct sum of W1 to WR. Okay. So W1 to WR, so basically this means, so what does this mean? The sum of Wi is whole of V, and W1 intersection, the sum of the remaining ones is 0, and so on. Yeah. Or in other words, any element in V you can uniquely write as sum of W1 plus W2 plus W3 up to WR. Yeah. So that is these are multiple ways of thinking about this as a thing. Yeah. Now let B1 to BR be basis of W1 to WR. Yeah. So B1 is a basis of W1, B2 is a basis of W2, and so on. And BR is a basis of WR. Yeah. Then we can talk about a matrix of phi with respect to So if these are the bases of W1 to WR, then you can club them together, these bases, one after another, yeah, and get a basis of V, yeah, because it's a direct sum, right? So B will be a B which is basically unions of B1 to BR clubbed together in, so it's an ordered basis, right? So we maintain the order. First, we look at the elements of B1, then elements of B2, and so on. So the matrix of V with respect to B is the block diagonal A1 to AR, yeah, and zeros where I can write where AI is the matrix. What is the matrix of which operator? AI? Say it louder. Phi restricted to WI. Yeah, phi restricted to WI. Yeah. So AI is the matrix of the of phi restricted to WI with respect to the basis BI. Yeah. So I mean, this is straightforward, right? So so should I? So maybe I'll just write one line, some proof. Note that if V belongs to BI, so ith basis, so ith basis of the ith W, then phi V is summation A I let's write it as JK BJ. J equals, I don't know. So what J runs over runs over number of columns, number of rows AI has, yeah. So let me not introduce more notation and let's write this way, yeah. So this is how phi V will be if because V belongs to BI means it's contained in WI, yeah. So phi V is in again in WI, so you can write it as VJ where VJs are in is in BI. Sorry, I have to write it correctly. So VJs are in are elements of BI. Yeah. So you can write phi V as a linear combinations of elements of BI because BI is a basis of WI, right? So this belongs to this belongs to WI. So that's why you can write it this way. And in fact, the way you can write it is depends upon the matrix AI. The matrix AI, which is matrix of E restricted to WI with respect to BI. Yeah. So other entries are zero. So above and below it will be all zeros. So the coefficients of all the vectors other than the ith vector will be other than the vectors in the ith basis is going to be zero. So that's why matrix of B with respect to B is block diagonal. Block diagonal with block matrices AI. Yeah, is that okay? Is that enough for the proof? Yeah, so we have done this for upper, I mean, when you have one invariant subspace of B, right? So it's the same proof more or less. Now we have a better structure, so we get a better matrix, yeah? Instead of block upper triangular, now we get a block diagonal. Okay, so this will be used in the sense that we will so to form the to find the Jordan form, we will do some sort of decomposition. Yeah. First into generalized eigenvectors and then. Okay, so let me. So I hope this is that part is okay. Yeah. So let's get into generalized eigenvector. Okay, so what is a generalized eigenvector? So it's a slight generalization of the eigenvector in the sense that for eigenvector phi of v should be lambda times b. Here we want some so basically phi minus identity of v phi minus identity should kill v. Yeah. So instead of asking that, we want some power of phi minus identity to kill v. So if that happens, then we say that phi is a generalized eigenvector. Yeah. So let V be a finite dimensional vector space and phi be a linear map on V with eigenvalue lambda. Then a non-zero element V of V is called generalized lambda eigenvector of phi if phi minus lambda I power n for some n when applied to V is 0. Okay. Is this clear? What is a generalized eigenvector? So we don't want phi minus lambda, not just phi minus lambda I to kill V. We want maybe some power of it. So of course, if V is an eigenvector, then it's of course a generalized eigenvector. Yeah, but generalized eigenvector could be bigger. Yeah. So we'll see why we came up with this notion in a bit. But first. Maybe I should have done that first. But anyway, I'll get to it. Yeah. Yeah. So yeah, since I've already written, yeah. So maybe I'll tell you why this is, or you'll see slowly why this is important. Yeah. So first, let's consider the set of generalized eigenvector of phi. Yeah. So you consider V lambda to be the set of all generalized lambda eigenvector of phi, and 0 is not there. So we don't consider 0 as an eigenvector, and hence also as a non. So you include 0, throw in 0 as well. Then this becomes a subspace, invariant subspace of not phi lambda, but of V lambda, but V. Yeah. So then it becomes a phi invariant subspace of the vector space V. Yeah, so V is given to B is given to you, and phi is a linear operator. So if you look at the set of generalized eigenvector and throw in 0, then it becomes an invariant subspace. Like the eigenspace as well. Yeah, eigenspace is also an invariant subspace. Generalized eigenvector is also generalized eigenspace is also. So you can think of it as a generalized eigenspace. Yeah. So this is also invariant subspace. Okay. Moreover, if the characteristic, so if you can write the characteristic polynomial of phi as product of linear factors, yeah. So for instance, that happens when the base field is algebraically closed. Yeah. So anyway, our Jordan forms exist only when you assume base field is algebraically closed. In fact, it will exist under this hypothesis more. Yeah. So moreover, if the characteristic polynomial of phi is product of linear factors, then you can write V as dx sum of V lambda 1 to V lambda r. Okay. So this is and these are all going to be invariant phi invariant subspaces. Yeah. So that already breaks. So if we take a basis of V lambda 1 and V lambda r, then we will already get some block diagonal. Yeah. And then we'll have to do a little more to get into Jordan form, but this will at least we can work with one of these V lambda i's. Yeah. And try to prove the Jordan form only for V lambda I, because it will be same for the others. Okay. So here lambda1 to lambda r are distinct roots of the characteristic polynomial. Yeah, so here we are considering lambda1 to lambda r are all different because v lambda only depends upon lambda, right? It doesn't depend upon the multiplicity of lambda in the characteristic. Okay, so we'll begin by proving this, and then maybe I'll come to this discussion about why this generalized eigenvector, what I mean, related to the Jordan form in some sense. Yeah. So first, let's make sure that all the I mean, we can restrict to the situation where we can assume that there is only one eigenvector value. Okay, so this will reduce to the case where there is only one eigenvalue, because then we can restrict phi to v lambda 1 and try to see how the matrix of this looks like with respect to some nice basis. Yeah? And then club them together to get a Jordan. Okay, so let's see why this is true. So first, why is this an invariant subspace? Yeah. So first of all, why it is a subspace and then invariant subspace. So let v1, v2 be two elements of v lambda. Yeah. So that means v1 and v2 are two generalized eigenvector. So that tells you that phi minus lambda I, some power of it kills vi. Yeah. So let's say n1 power kills v1 and n2 power kills v2. Yeah. Then you can take n to be max of n1 and n2. And then, of course, phi minus lambda I will kill both v1 and v2. The nth power will kill both v1 and v2, and in particular, any linear combination of v1 and v2. Yeah. So that tells you that any linear combination of v1 and v2 is either 0 or a generalized eigenvector. Yeah. Of course, 0, of course, maps to 0 under any linear map. But any generalized eigenvector is a linear combination of any generalized eigenvector is either a generalized linear eigenvector or 0. Yeah, so that proves that v lambda is a subspace. Is that okay? Yeah. So now we'll have to show that this generates whole of v, and it's an internal direct sum. Yeah, so there is no intersection among these v lambdas, and it generates the whole of v. Okay. Oh, and we also first we'll have to show that is phi invariant. Yeah, and then we'll get to it. Yeah, so to show phi invariant is straightforward. So we'll have to show that if I take phi of something in v lambda, then it lands in v lambda. Yeah. So let's take v1 in v lambda. Yeah, like we did earlier, and apply phi to it, and then apply this phi minus lambda I power n1. Yeah. Then you see it's this phi commutes with I. Yeah, everything commutes with the identity matrix, and phi of course commutes with this phi itself as well. Yeah, phi square is phi square. It doesn't. There is nothing to. So we can pull out this phi on the other side. Yeah. So phi minus lambda I power n1 is same as a composed phi is same as phi composed phi minus lambda I power n1. Yeah. So phi commutes with phi and phi commutes with I, so it commutes with phi minus lambda I, and hence we can move things one by one, and hence to the whole of n1. Yeah, so we get that this happened, but phi minus lambda I power n1 v1 is 0, and phi is a linear map, so it sends 0 to 0. So it tells you that phi v1 is killed by phi minus lambda I power n1. Yeah. So that tells you that phi v1 belongs to v lambda. Yeah. So that tells you that phi is v lambda is phi invariant. Yeah. So that tells us that these v lambda 1 to v lambda r, each of these for lambda 1 to lambda r distinct roots of the characteristic polynomial are all invariant. Yeah. Now we have to prove that they sort of the direct sum of them is whole of v. Yeah. So now onwards, the proofs are a little more tricky, but maybe not too bad. Yeah. So look at the characteristic polynomial of phi. So it looks like t minus lambda 1 for m1 to t minus lambda r for mr. Yeah, because these are all the distinct roots of the characteristic polynomial. So say it appears with lambda 1 appears with multiplicity m1, lambda r appears with multiplicity mr. Yeah. So the characteristic polynomial is going to look like this, right? So what do? We define two polynomials. Yeah, we want to somehow. So you see why it will give us some sort of projection maps onto two factors, and that will help us. Yeah. So we'll sort of use induction on the dimension of V in some sense, or the number of roots, if you like. So of the characteristic polynomial. Well, maybe dimension on V is simple. Yeah. So consider this polynomial. So what you do is you remove one of the factor. So Gi is t minus lambda I for mi. Characteristic polynomial of phi divided by this factor. Yeah. So you are keeping all the factor except for the ith factor. Okay. So Gi is again a polynomial. I've written it as a ratio, but basically what I'm doing is removing one of the one of the one of the eigenvalues in some sense. Yeah. And Fi is the other piece, yeah, t minus lambda I power mi. Yeah. So basically Fi times Gi is the characteristic polynomial again of phi. Okay, so this is what we have defined. Gi is Fi is t minus lambda I power mi, and Gi is basically characteristic polynomial divided by Fi. Okay, so these are the two polynomials. So their product, of course, is the characteristic polynomial, and their GCD. So you can they don't have any common factor. Yeah. The Gi and Fi, they don't have any common factor. So Fi has only one kind of factor, t minus lambda, some power of t minus lambda I, and t minus lambda is not a factor of Gi because we have removed all powers of that. Yeah. So once you have some two polynomials with coefficient in a field, and they don't have any common factor, then you can write down. So you can find polynomials such that their linear combination is 1. Yeah. So this is like in the integers. Yeah. So if I give you two co-prime numbers, then you can find AB integers such that so if I give you two co-prime numbers P and Q, yeah, then you can find AB such that AP plus BQ equals 1. Yeah. The way you do it is use the long so you use the division algorithm, right? You keep on doing the division algorithm, and eventually you'll get 1. Yeah, because I mean you can't if you get something which bigger than 1, then that means that that will be a common factor for both P and Q. Yeah. So you apply the same algorithm. So division algorithm applies even in what ring in which division algorithm applies is called a Euclidean domain. So if you know what Euclidean domain, do you know what a Euclidean domain is? Okay, so how do I see figures? Yeah. So how many of you know Euclidean domain? You don't know Euclid. So then just think of it as a division algorithm. Yeah. So we saw this remainders theorem or division algorithm. Yeah, you can divide by something and you'll get a remainder. Yeah. Then with remainder as your quotient divisor and the previous divisor as your thing which you dividend maybe you again carry out the division algorithm and so on. This is how you sort of find AB, yeah, for in integers. So you keep doing this, and eventually you'll get that the remainder is 1. Yeah, if you don't get remainder is 1, and you get remainder 0 without getting I mean with remainder having higher degree, that means it must have a common factor. Yeah, like in P and Q. So similarly here it will have the same property. Okay, so you can carry out. So maybe this is something you can do as a homework problem. So maybe I'll build a homework problem around it rather than doing it here. Yeah. So this is sort of like a high school kind of problem. So I'll make a homework problem with respect to this, and you can try to instead of using. So ideally, you can make this into something some abstract notion. This division algorithm into something abstract, and that is what the Euclidean domain is. Okay. So maybe I'll make a small homework about it. But the point is, you can find so upshot of all this is you can find polynomials a and b such that fi plus bgi is 1. Yeah. So here I is fixed. I is some. So you fix some I. So I could have taken I to be 1 and worked with yeah. So okay. So now I haven't really proved this. Okay. So now you consider pi to be bgi phi. Yeah. So b times gi is a polynomial, and you apply phi to you evaluate it at phi. Yeah. So you will get a endomorphism. So phi was an endomorphism of v. So when you apply, you plug in into a polynomial, you get another endomorphism. Yeah. So that is what our pi is. Yeah. So yeah. So then what I want to say is that pi is a projection operator onto v lambda I. Okay. So let's see why that is true. I could have written more, but anyway. So okay, so let's see. So pi is this thing. So yeah, so it is okay. So basically, this fi will sort of kill um, um, yeah, fi will kill v lambda I, so bgi will be yeah. Okay, so let's see. So this is correct. So let's see a proof. Ayo. 1 second. Something. Yeah. So yeah. Okay. Now you can see the screen again. Yeah. Okay. So let's see why pi is a projection operator, and then it will become slightly easier for me. Yeah. So yeah. So gi basically kills everything other than so let's see. So we'll have to check pi square is same as pi. Yeah, and the image of pi is in v lambda I. Okay, that is all we have to check. So let's see what is pi's. Uh, uh, yeah, so I have to write it pi square is So pi square is pi compose pi. So let's just so maybe I didn't think this through. So pi compose pi of is so I have to do b gi. So this is a polynomial b times gi evaluated at phi. Yeah, and yeah, so it is okay. Yeah, so um, um, okay, it's okay. Yeah, so this is same as AFI plus BGI times BGI phi. Yeah, because AFI plus BGI is just one. So multiplying this polynomial by one doesn't change anything, right? So it is same as this thing, right? Now, now you just multiply this through. So this is AFI. So, or maybe since it's all polynomials, so we can write it in any order. So let's say AB FIGI evaluated at phi plus BGI whole square evaluated at phi. Yeah. So I'm just writing pi right now, not pi square. Yeah. I'll get to pi square. So this is basically the other term is pi square. So, but what is this? This is AB, and what is Fi times GI? It's the characteristic polynomial of phi evaluated at phi, and this is BGI phi and compose BGI phi. Yeah, right. So and characteristic polynomial of phi evaluated at phi is 0 by Kelly Hamilton, and this is precisely p square, pi square. Yeah. So we see that pi square is same as pi. Yeah. So we sort of did it in some abstract way, but we got that pi square is pi. So we see that pi is a projection. Yeah. And then we also have to look at image of pi. So I want to say that the image of pi is precisely precisely v lambda I. Yeah. So so yeah, so let's show that. So let V belongs to V. So we'll do it in. We'll prove the two inclusion. Yeah. So let V belongs to V lambda I. Then we want to show that it lies in image pi. Yeah. Um, yeah. So what do we have to show? So yeah. So so I have to show it is in image pi. Yeah. Um, yeah, so of course I can always write V as A Fi plus BGI evaluated at phi. So this linear operator, which I'm basically, which is identity, right? Because this is the one polynomial evaluated at V. Yeah. But the point is, I can split it. Yeah. So this tells you that this is A Fi phi plus BGI BGI phi of V. So this is PI V. P and V. Yeah. Now the point is this AFI phi is what? This is A phi minus, so fi is, remember this is t minus lambda I power mi. Yeah. So phi minus lambda I for mi v plus piv. Yeah. And v belongs to v lambda I. Yeah. That means v is scaled by some power of phi minus lambda I. But we are claiming that is scaled by mith power. Yeah. So what I'm trying to say is this will be z. So this is 0 plus piv. Yeah. So here I'm saying that not just some power, just mith power will be enough. Yeah. So this will be a homework problem. So I'll let you do this homework. Okay. So I'll put this down as a homework that if the characteristic polynomial has the factor so is of this form t minus lambda I power mi, and the remaining is co-prime to t minus lambda I. Yeah, then you just need to do mith power to get all the generalized eigenvector. Yeah, to kill all the generalized eigenvector. So that assuming that homework, you get that v anything in v is actually in the image of PIV, and conversely. So of course the converse is easier. So if v belongs to image PIV, image PI implies v equals PI v tilde for some v tilde in v, which is b gi phi of v tilde, because that is what pi is. Yeah, and then so I want to say that it belongs to v lambda I. So I just have to show that it's killed by some power phi minus lambda I power something. Yeah. So you multiply it by instead you can multiply it by just t. Yeah. So this is so now you multiply by phi minus lambda I for mi of v. Yeah. You apply this. So this is going to be from by this previous line. It is b times of this fi was fi is that polynomial. Yeah. So b times fi gi. I can write it in whatever order. Yeah. P of v tilde. Yeah. But fi times gi is the characteristic polynomial. When you apply phi, you get 0. Yeah. So maybe one more line. So this is b times ch phi, and then v tilde. But that, of course, we know is 0. Yeah. So this tells you that v belongs to v lambda I. Yeah. Okay. So we got that pi is a projection operator on v lambda I. Yeah. Is that okay, everyone? So we proved that pi square is pi, and the image of pi is v lambda I, and hence it is the projection operator on v lambda. Okay, so now we are still trying to prove that v is the direct sum of v lambda i's. Yeah. So so now it will be easy. So I'll apply this induction argument. So we can factor out one v lambda one out of it. Yeah.
Sir?
Yes.
Can I ask a doubt?
Say that again.
Can I ask a doubt?
Yeah, please.
The last portion that you proved just now.
Yeah.
Are you confused at the first step where phi minus lambda I power mi of b is written like that?
So phi minus lambda I power miv, but is same as okay. So maybe I'll do it in 2 steps. Then it will be easier. Yeah. So let's just. I'll have to erase because maybe this is better. Yeah, so V is V GI phi applied to V tilde. Yeah, and you are applying this thing. Yeah, so this is same as F phi compose this. Yeah, is this okay? Because F is what? T minus lambda I for mi. Fi is, sorry, F is Fi. Fi is T minus lambda I for mi, right? So Fi phi is precisely this. Yeah, and so this is same as F B F G, this polynomial evaluated at phi, and then you apply V tilde. Is this okay? And this is the there's B as well, but doesn't matter. V tilde, which is C. Now better?
Yes, sir.
Any other question?
No, sir.
Okay. Okay, good. So let's. So now we have proved that Pi is a projection operator. So now we will use it to show that we can decompose V into these things. Yeah. So what you do, yeah. So let's say W. I have to write darker. So let's say W is the kernel of our, yeah, so let's now fix is the kernel of P1. Yeah, maybe let's call it W1. W1 is the kernel of P1. So yeah, then what do we know? We know that V is V lambda 1, which is the image of P1 plus W1. Yeah. And this, and of course, V lambda 1 is phi invariant subspace, and W1 is also a phi invariant subspace. Okay, why is W1 a phi invariant subspace? Any guesses how you can think of W1 as a phi invariant subspace? Or can you think of W1 as image of some linear operator? Like we saw, V lambda 1 was image of BGI phi, yeah? Or BG1 phi in this one. B lambda 1 will be BG1 phi. So what will be the, which linear operator's image will be W1? So you just take the other factor, AF1, yeah? So if you consider AF1 phi, yeah? Let's call F1, yeah? So let's call it Q1. So I should have just done it with 1 instead of I, yeah? So you consider this Q1, yeah? Then Q1 is again So in fact, you can also show that Q1 is again a linear projection operator in the same way, more or less. But anyway, what you can see is that P1 plus Q1, what do you know about P1 plus Q1? What map is P1 plus Q1? So maybe we stick to I, yeah, because I have fixed this A and B were related to that I. So let's just stick to I, yeah. So QI. So what is PI plus QI? I mean, just think in terms of phi, how can you write a PI plus QI?
PGI of P plus AFI
Yeah, so what does that tell you?
is equal to 1.
Yeah, so that polynomial is 1. So if you evaluate phi to a 1 polynomial is the identity matrix, right? So PI plus QI is in fact identity. Yeah. So that is why, so what you get is that this W, the point is you can check that W image of, yeah, so let's say something which lies in, so basically QI is identity minus PI, yeah. And so if something, so we wanted to say that W1 is, so if I prove, so first we prove that W1 is in image of Q1, yeah. So WI is image of, yeah, WI is image of QI, yeah. So so let's say W belongs to WI, yeah. Then QI of W is what? It's W minus PI of W. And what is PI of W? WI is kernel of PI, yeah. So anything which is in WI will go to 0, yeah. So this is just W, yeah. So that tells you that basically we have decomposed the map itself, identity as PI plus QI, yeah. So you get that QI of W is W. So that tells you that I mean, that tells you that anything in W is WI is in the image of QI, yeah, because QI pretty much on WI is identity, yeah. So and conversely, so if you take yeah, so anything so if something is in WI, so W belongs to image QI. That means W equals, so this will tell us, this will imply that W is QI of some W tilde, yeah, for some W tilde in V. I want to show that W is in WI, yeah, so that I can have that QI is image of QI is same as WI, yeah. So So we get this is identity minus pi of w tilde. So this is the w tilde minus pi of w tilde. But w tilde is something in v. Yeah. So you can write a unique. You can write it uniquely as something in v lambda I and something in wi. Yeah. So this and whatever it is in v lambda, so it is a projection onto v lambda I. So so whatever it will be, so this belongs to wi. Yeah, because w tilde you can write it as, let's say, x plus y, where x belongs to v lambda I and y belongs to wi. Yeah, because it's a direct sum, right? We already saw that v is v lambda I plus so we can write, I always write it as kernel plus the image. Yeah. So we have this. So and pi of w tilde will be precisely x, right? So w tilde minus x will be just y, which is in wi. Yeah. So we see that image. So if you know how this projection things work, these are obvious. But since you guys don't know that much, you haven't seen that much ring theory. So that's why I'm doing it in a more concrete way. Is precisely wi. Yeah. Now, of course, but qi is afi phi. Yeah. So phi times phi composed qi is same as qi composed phi, right? Because qi is since qi is given by a fi evaluated at phi. Yeah. So polynomials commute, so it doesn't matter. Yeah. So phi times qi is basically t times afi evaluated at phi. Yeah. So you put t before or after, it doesn't matter, right? So you get this. So this is same as saying that. So hence. Phi of image qi is equal to is in fact contained in image qi. Yeah, qi. Okay. So that tells you that wi is again so which is wi. So that tells you that wi is a phi invariant subspace. Yeah. So we have decomposed it into two phi invariant subspaces, v lambda I and wi. Yeah. So we can look at now. So we know what happens in v lambda I. Yeah. So when we restrict phi to v lambda I, we know that the only eigenvalue is lambda I, right? So phi restricted to v lambda I is a linear operator with eigenvalue lambda I. Yeah. Because it consists of only generalized eigenvectors. Yeah. Lambda I generalized eigenvector. And phi restricted to wi is a linear operator on a smaller dimensional vector space. Yeah. And so is a linear operator on w okay. And if we show that wi is direct sum of lambda v lambda 2 to v lambda m, then we are done. Yeah. So take I to be 1, takes I equals 1. Yeah, so if we show that phi restricted to W1 is direct sum of V lambda to V lambda M, then we are done. Yeah. So here is what happens. So now you look at the characteristic polynomial. So let's call this phi prime. Yeah. So characteristic polynomial of phi prime T is going to be what? Yeah. So I mean, if you think about phi um, as a linear operator on whole of V, we have decomposed it into yeah. So there is okay. Yeah. So this is going to yeah. Okay. So first of all, yeah. So there is still some work to do. Yeah. So the point is, yeah, I want to say that the characteristic polynomials auto splits. Yeah. So this is going to be yeah. So maybe I should have written a little more. So this will be GIT. So G1T. Okay. So you have to remove the lambda 1 factor, and characteristic polynomial of phi restricted to V lambda 1 is precisely F1T. Okay. So so this is not too bad, but requires a bit more argument. Yeah. So of course, yeah. So yeah. See the character. So here we get that the sum of the mi's is the dimension. So the characteristic polynomial has degree same as the dimension of V. Yeah. So the sum of the mi's is the whole dimension V. Yeah. And so yeah. Maybe yeah. So we should use the decomposition. Yeah. So hi. Yeah. Yeah. So um, yeah, so let's write down the matrix of V with respect to some basis of V lambda 1 and and some basis of W. Yeah. So so matrix of phi with with respect to B1 basis of V lambda 1 and B2 basis of maybe there is a small simpler way. Yeah, so I'm trying to make things more complicated than it should be. 1 second. Let me see, I can pull out from here itself. Because I've already proved that PIs are linear projections on V lambda 1 to V lambda n. So that might be enough. So I mean, what I'm trying to do may work as well, but will work as well, but maybe there is a simpler way because I've proved something stronger. Yeah. No, but I've only proved that BG1, yeah, plus AF1. Yeah, so I haven't really, yeah, so maybe I'll have to do a little more. So this induction step, I'll have to So see, once I prove that the characteristic polynomial of this is G1T, then I can apply the induction hypothesis and say that W1 you can write it as the sum of V lambda 2 to V lambda m, and hence the whole of V will apply. Yeah. So let's try to prove that the characteristic polynomial is indeed this, and then we will be done. Yeah. Then we will apply induction hypothesis. So is going to be some matrix A, and let's call this let's call it A and C. B is for basis. So we'll get block diagonal A and C, where A is the matrix of phi restricted to V lambda 1 with respect to, and this is matrix of W1 with respect to V. A is the matrix of phi restricted to V lambda 1 with respect to V1.
Wait, I'll give one and get back the other.
Yeah. Okay. So where A is the matrix of phi restricted to V lambda 1 with respect to B1. Okay. I stopped writing. I sort of stopped writing. 1 second. Okay, maybe it will work now. Okay. B1 and C is the matrix of phi restricted to W1 with respect to B2. Yeah. So okay, so we got this much, and then the characteristic polynomial of phi with is basically the characteristic polynomial of phi restrict. So maybe one could have done this characteristic polynomial of phi with restricted to V lambda 1. Okay, maybe I could have done it without this matrices. Yeah, so is the determinant of A minus lambda I times the determinant of C minus lambda I. Yeah. So A minus Ti times the determinant. So it is P restricted to W1 is phi prime. Yeah. So let me just write it this way. Right. So and now the characteristic polynomial of phi restricted to lambda 1 is this thing. Yeah. So okay. So yeah. So why is that? Yeah. So note. The point is. Yeah. So maybe this is not too bad. Yeah. So see all the lambda 1 eigenvalues of all the lambda 1 eigenvectors of phi are in V lambda 1, right? So so this W1 does not contain W1 is a complementary subspace, right? So it doesn't contain any lambda1 eigenvector. Yeah. So that tells you that lambda1 is, I mean, phi restricted to W1 doesn't have lambda1 as a eigenvalue. Yeah. So note phi prime doesn't have lambda1 as an eigenvalue. Yeah. Since phi restricted to W1 does not contain yeah. So rather phi prime is same as phi restricted to W1. Since eigenvectors lambda1 eigenvectors of phi1 are since lambda1 eigenvectors of phi are in V lambda1. Yeah. So it cannot have. Yeah. So that tells you that the characteristic polynomial of phi prime does not contain V minus. Yeah. So that tells you that characteristic polynomial of phi prime divides G1t. Yeah. G1t was characteristic polynomial of phi divided by F1t. So it cannot have t minus lambda1 as a factor. Yeah. So it has to. So this must divide characteristic polynomial of phi divided by F1t. Yeah. So it must divide this, and but also we know that the characteristic polynomial of yeah. So phi restricted to V lambda1 minus ti for m1. Yeah, if I look at this rest is 0. Yeah, or maybe let's just put this outside. Yeah, so restricted to V lambda1 is 0, right? By that homework problem, that you only need m1. So it doesn't matter whether you need m1, but some power will when we apply to V lambda1 is going to be 0. Yeah. So that tells you, this implies that the minimal polynomial of V lambda1 has only lambda1, not t. Lambda1 I for m1 is 0. Yeah. So that tells you that the characteristic polynomial or the minimal polynomial, minimal polynomial, and hence the characteristic polynomial phi restricted to V lambda phi restricted to V1 has only t minus lambda1 as a factor. Yeah, as a linear factor, or is of the form some power of this. Yeah, is t minus lambda1 power something. Yeah. So I don't know which power. It may be smaller than m1. I'm just proving that some power of this skill set. So minimal polynomial has to divide it, and so the minimal polynomial has only t minus lambda1 as a factor, and hence minimal polynomial is some power of t minus lambda1, and hence characteristic polynomial is also some power of t minus lambda. Yeah. But that is good enough. Yeah, because so hence characteristic polynomial of phi prime t is G1t. Yeah. So because because of this identity, because we know that t minus lambda1. So see, the first factor has to have a factor t minus lambda1, some power of t minus lambda1. The second factor cannot have t minus lambda1. Yeah. So that tells you that and characteristic polynomial of phi t is t minus lambda1 power m1 times G1t. Yeah. So of course, the second factor then must be G1T, and the first factor has to be T minus lambda 1 per m. Okay. So that's it. So now use induction. Use induction. Oh, this took too long for me to get to Jordan forms. Use induction to show that. So see, W1 is a vector space, and phi prime is W1. So how are we using show? Now use induction, but let me just get this set up. Induction to see the result. Since dimension W1 is less than dimension V, and phi prime is a linear operator on W1, and characteristic polynomial of phi prime evaluated at T is T minus lambda 2 for M2 to T minus lambda M for MR. Yeah. Hence, W1 has to be V lambda 2 direction V lambda. I mean, it should be W, but W1 is W lambda 2, W lambda R. But I mean, W lambda 2 is going to be same as V lambda 2 plus V lambda R. Because on V lambda 1, these are not nil. I mean, T minus lambda 2 will not. Yeah, so maybe this this also one has to work. Yeah, so maybe this I'll assign as homework. Yeah, that W lambda 2 is same as V lambda 2 in this setup. Okay. So maybe, yeah, because this otherwise, yeah, I made. So maybe I should have proved some propositions and then got to this thing. Okay, so so unfortunately this proof looks too long. Yeah, but so maybe I should have thought a little more and broken it up a little bit. But we do get that this breaks in. So go over this proof again, yeah, maybe. And if you have questions, you can put it in the comments in the classroom portal, yeah, and I'll try to answer. But to modulo this homework, so in fact, yeah. So modulo that these two homeworks, this is okay, yeah. So the point is every vector in W lambda 2 is contained in V lambda 2. You'll have to argue the other way is also true. Yeah, everything is in V lambda 2 is also in W lambda 2. And that also follows because the only thing missing is in V lambda 1 and those things will not. So it will come out this way. Okay. Yeah, so yeah, so I was hoping I'll say something about. So maybe I'll do one example of what I was trying to. So I was trying to tell you something about the generalized eigenvector, eigenvector. Yeah. Where did it go? Yeah, so something about the generalized, why we are looking at the generalized eigenvector and so on. So maybe I'll, yeah. Or let's, yeah, so. Yeah, so let's do one example of this. What happens when you have a generalized eigenvector? So maybe one proposition which will sort of give you some understanding about what we are trying to do. So how this will help, yeah. So let phi be a linear operator on V, and lambda be an eigenvalue and V be a generalized eigenvector of phi. Okay. So that tells you that t minus lambda I power n is going to be 0 for t minus lambda I power n evaluated at V is going to be 0. So let me define something more. Yeah. Let n be the least positive integer such that p minus lambda I for n V is 0. Yeah. So that means phi minus lambda I power n V is 0, but phi minus lambda I power n minus 1 V is not 0. Okay. Then we'll call it n is called the exponent of V. Is called the exponent of V. Exponent and of the generalized eigenvector V. Vector V. So if the exponent is 1, then you say that it's an eigenvector. Yeah, that means just phi minus lambda itself is. Yeah. So now the result I'm trying to say is that you look at V and so V phi minus lambda I V phi minus lambda I square V and so on up to phi minus lambda I for n minus 1. So that up till that this is non-zero. Yeah. So you consider this set. Yeah. Then this well, let's call it B. Yeah. So then B is a basis is a linearly independent set. It's a linearly independent set. Okay. And so let's say W is the span of B. Then let W be span of B. Then phi W is contained in W, and the matrix of phi restricted to W with respect to B is, so what will it be? So yeah, so you can check, it will be if you apply phi to V, then it becomes yeah, so it will be this thing. It will be this Jordan matrix. Okay. So so somehow we will in each of these V lambdas will produce bases like this, and then we will we'll produce linearly independent sets like this, and we'll get Jordan blocks. Yeah. So why? Yeah. So maybe let's see why this is true. So this is not true. So let's call this. Yeah. So maybe let's call this V0, V1 up to Vn minus 1. Yeah. So yeah. So V0, of course, is linearly independent because V0 is a generalized eigenvector. Yeah, that means it's non-zero vector, so it's linearly independent. What about V1 and V0? So so we'll have to say that V1 is not a linear, is not a multiple of V0. Yeah, but yeah, so and then V2 is not a linear combination of V0 and V1. So these are yeah. So this is V2 and so on. So yeah, so maybe so first basis and then okay. So I'll come to it, but let's see what happens to phi V0. Phi V0 is basically you can so you can is let's look at what is V1. Yeah, so maybe V1 is phi minus lambda I of V. V which is so V is same as V0. Yeah. So let's this was V. This is V0. So I can put it as V0, and this is so phi V0 minus lambda V0. Yeah. So what we see is that phi V0 is basically V1 plus lambda V0. Yeah. So from this equation, we get that phi V0 is V1 plus lambda V0. Yeah. So in fact, phi of Vi you can is basically so similarly V2, if you think about it, it's is phi of lambda I times phi of V1. Yeah. So this is phi minus lambda I phi of Vi minus 1. Yeah. So this is so and yeah, so no, this is not what I meant. Plus lambda I phi of Vi minus 1. So I'll have to cancel this plus yeah. Yeah, so this is so I've subtracted minus lambda I phi of Vi minus 1. So I have to add this as well to cancel it out. So this becomes and so this is precisely what am I getting? No, this is not what I wanted. Yeah, so let's not write it this way. So what I wanted is Vi is phi minus lambda I times phi of Vi minus 1. If I mean, unless if I shouldn't be too big. So if I is less than n minus 1, yeah, then if I is equal to, so if I is less than n, yeah, then this is good. Yeah, then because if I is equal to n, then phi of Vn minus 1 will already go across, yeah. So will become 0. So I less than n minus 1. Unless it's the border situation, we get this. Yeah, so this, yeah, so so we get, from here we get that Vi is phi of phi f. Something is wrong.
Sir,
There is no phi here, yeah. Yeah, this is right, yeah. Now it will be okay. So this is phi of Vi minus 1 minus lambda Vi minus 1. Yeah. So we again see that phi of Vi minus 1 is again Vi plus lambda Vi minus 1. Yeah. So this tells you that so the first line tells you that phi of V0 you can write it as as yeah, so I think I'm getting the matrix to be not this, but one should be below. Yeah, so instead of above. So yeah, so it should be here. Yeah. So phi of V0 you can write it as lambda times V0 plus V1. And in general, phi of Vi minus 1 you can write it as lambda times Vi minus 1 plus the next guy, Vi. Yeah. So once we prove that this is linearly independent, the matrix is clear. Yeah. From these calculations. So the only thing one has to check is that this is linearly independent. Okay. So maybe so this is also not too bad. We just have to check the linear, but maybe I'll do this next time. Okay. So it's almost 1. So let me stop here, and then on Wednesday I'll do this and then complete the proof of the Jordan form as well. Okay, so let's stop here.